Sweet. All right, nobody cuss. Here's kind of what the chain rule says. And then I'll go through some examples. These symbols probably aren't going to make a lot of sense, but this is how you write a composition of functions. It says start with function f, substitute g in for the x's in function f, which you could write like this. And then the way you take the derivative is the same way you eat a peanut M&M. First you bite through the candy shell, then the chocolate layer, then the peanut. So I'm going to do the derivative of this thing, then this thing, and then of that thing, whatever that is. One at a time, kind of in layers from out to in. And that's what this says. Start with the derivative of f, then multiply that by the derivative of g. Hard to understand what that means. I'm going to skip over the fraction part. We'll come back to it if we need to. Here's an example. So, do you know how to expand 5x plus 3 squared and then do the derivative? Do I need to take the time to do that for you? You know, I will. It'll be good practice. So, 5x plus 3 squared, I would write multiply those out, you get 25x squared. Now I'm going to skip one, I'm not going to show one step, I guess. I'm going to multiply 5x times 3x to get 15x. But then I'm going to also multiply 3 times 5x to get another 15x. I'm just going to multiply those and go ahead and combine them to get 30x's, which is a pattern that always works when you square a binomial. It's the square of the first and then 2 times what you get when you multiply each term together and then the square of the last. But you could just do this. This is f. And then you have to take the derivative, which is not hard. It's all power rule. Roger that. Shouldn't be anything new there. Let's do the same problem using the chain rule. For the chain rule, I'm going to take the derivative of one layer at a time, not changing anything on the inside until I take the derivative of the inside, okay? So here's what I mean. If you look at this function, 5x plus 3 quantity squared, the outermost mathematical operation is that square. I'm going to take the derivative of a square, which would be 2 times that thing raised to the 1 power, right? But I'm not going to change what's inside of the square just yet. That's the power rule. Then the chain rule kicks in and says, hey, after you do the derivative of the outer function, multiply what you get when you take the derivative of the inner function. Well, 5x plus 3 is on the inside. What is the derivative of 5x plus 3? 5. So I'm just going to multiply this by 5. The 1 power, I don't really have to write, which means I can just distribute the 2 and the 5 to the stuff in the parentheses. Well, the 2 times the 5 is 10, so I'm really just multiplying 10 by these. 10 times 5x and 10 times 3. Now, it's not significantly shorter on this because I showed all the steps, but chain rule's kind of nice, especially if you have to expand a polynomial. Roger that? Does it make a little bit more sense what I mean by take the derivative of the outer function, then multiply that by what you get when you the derivative of the inner function? Yeah. Here we can maybe do a couple more. In example 2, the outer function is the cube. That's power rule. The derivative of something to the 3rd power is 3 times that thing to the 2nd power. Well, what is the thing? 4 minus x squared. And the chain rule kicks in. The chain rule is always kicked in. You multiply this by the inner function. So now I want to do the derivative of this piece. Well, the derivative of 4 minus x squared is just negative 2x. Before today, you couldn't do the derivative of this without an extreme amount of work. You would have to multiply out 4 minus x cubed 3 times. That's a lot of distributive property. And then do a whole lot of power rules. Chain rule helps with that.
Okay, so what do you mean when you say that the x and the squared are outside functions?
I want to redefine this problem to see if this makes sense. I could say, hey, I have a function called g. And the function g is going to be x to the 3rd power, okay? And then I could define another function that I'm going to call h. And I'm just picking these letters at random. And function h is going to be 4 minus x squared. Now, I can build the function f using g and h. I would say, well, function f then is you start with function g and you put the function h in for its x's. I want to take this stuff and put it right like a substitution problem, okay? So I would call this, that's composition. What I mean by outer function is g, and what I mean by inner function is h. It doesn't have to be powers. It could be trig functions. It could be logarithms. It could be exponentials. Does that make a little more sense?
Does that mean that any term that is cubed or squared is considered its own function?
Yes, ma'am. Now, based on what I just did, there's a slight modification we might need to make to the power rule. If you're doing a function raised to the power, then obviously you're going to move the power to the front and subtract 1 from the power, like we've done before. But then you have to add in, let me take that back. Then you have to multiply by the derivative of that inner function because of chain rule. All the examples we've done so far, that inner function just had an x to the 1st power. Well, what's the derivative of x to the 1st power? So we have been using chain rule. It's just been defaulted to 1 every time, and multiplying by 1 doesn't really do anything. And here's what the exponential rule would look like. It would still be e raised to the g of x, but then you're going to have to multiply by the derivative of that exponent if that exponent is a function, which it will be. Roger that, Ms. King? You good?
Yeah, sorry. I promise I was listening.
It's okay. It's all right. So we should probably do a couple of these. Are any of these actually in? Let's do this one. And we can do more of them, but I think this will be a good way to see. So can I convince you in this problem that the outer function is the e to some power? So I want to do the derivative of, I want to start this derivative with the derivative of e to some power. Well, the derivative of e to some power is e to some power. And then I have to multiply this by the derivative of the inner function. In this case, the inner function is the exponent, so I need to multiply by the derivative of 3x squared, which is 6x. Now, most people don't write the linear term after the exponential term. There's nothing wrong with doing that. But in general, the way you're going to see these written, most likely, you're going to have the coefficient and or linear term in front of the exponential term, which is why the rule is written the way it is with the g prime in the front. But I would encourage you to approach it the same way you do all composite functions with chain rule, work from the outside in. That way you're doing the same process every time.
What about for A?
Oh, let's do A. Here, let's go through it. Let's go through it. But before I do A, is everybody good on D?
So that's just like our answer, we don't have to go any further.
Nothing else we can do.
Wait, I'm still confused on why on that one was E. Like, how do you decide what's your outer function, what's your inner function?
So there are two things going on here. What I want to do is I want to use F and G in order to build e to the 3x squared, right? So I'm going to write this two different ways, so see if it helps you kind of visualize what's going on. If I write g of f of x, if this is the way I think it should be written, I start with function g, I take out its x, and I replace that x with function f. So in this case, the outer function would be g. I would do the power rule first. But is that the correct composition? No, 3e to the x squared is not my original problem. So let me try to reverse those. This composition says start with function f, which is e to the x. Replace that x with function g, which is 3x squared. Is that the correct composition? Yeah. So I want to start with the derivative of the outer function, which is function f. Well, what was function f? E to the x. So I'm going to do an exponential derivative first. Does that make sense? Yeah? I don't really know of a better way to help you see it, but it kind of sucks.
That's good.
Okay. A, is that what you said? A. Do you see that there are two, potentially three functions here? I could say I have a square root, and then inside the square root I have a cube, and then inside the cube I have an x squared minus 1. Potentially 3, right? Which means I would just do the derivative of the square root, multiply that by the derivative of a cube, and then multiply that by the derivative of x squared minus 1. But I can save myself a little work. If I count all of that as one function. Can I do that? Can I rewrite this problem? Yes. Here, let me just show you what I'm thinking. Here, I just rewrote the radical like we've done, 10 or 15 times at this point? But see, now I just have two functions. I've got the power 3/2, which is a power rule, and I have the x squared minus 1. Which of those is the outer function? The exponent. So the way I do the derivative of an exponential, there's the derivative of the exponent. Now when I do the derivative of the outer layer, I don't change the inner workings just yet. But then I multiply. And I go in a level. So when I go in a level, now I'm doing the derivative of this thing, x squared minus 1, which is just 2x. Roger that? Can I cancel the red 2 and the black 2? This 2 and this 2. You see I can cancel those? The black 2 that I've got with the red dot is multiplied by 2. The red 2 is divided by 2. So I could pretty quickly simplify this and just have Here, I'll write it. Could have that. Or I could put the x squared minus 1 under a square root. Any questions about that? About this whole layer business or the outside or the inside? You good, Mr. Wilson? Makes sense. Ms. Hafer, you good back there? Ms. Moore? Harold? King? Skinner?
There you go.
I knew the name. I just looked at you. I thought you were going to say it. You good on that, though?
Yeah.
Mr. Bracken?
Oh, yeah.
Oh, yeah. You know why? It's not easy. Yeah, it's not easy. Do we need to do any of these? Here, I'm going to delete them because this is from old work. I don't want to say that I went through them with you guys.
We should do B or E.
B or E? Let's find a freaking tough one. B's too easy. You know what? We might do both of them. E? You want to do E?
Yeah.
Yeah, E is what we did just a second ago, but with a fraction.
And a negative. Right? And a negative. We'll do E. And if it's like, oh, I don't get it, we'll go back and do B. All right. Whew. There are essentially, here's what you got. You've got maybe a quotient rule. If you want to do a quotient rule, that would suck. When you do the derivative of the denominator, you've got this radical and you have the 6x when you do the derivative of the bottom. Or you could rewrite this problem using negative exponents. Here's the rewrite with positive exponents. That cube root is just a 1/3 power. I'm like, still doing quotient rule, not really feeling it, Mr. Dubose. So here's the rewrite. Plus 3. Now I don't have to deal with quotient rule. I can just do the derivative of the outer layer, which is the power rule. Here's the order that I would do things in. I would use this power rule first, and then I would do the derivative of that second. Roger that? You could do the derivative from here. Not really recommending it. You might want to try it on, see which one you like. So here we go, y prime. I'm going to move this exponent to the front and multiply it by that number. Well, when you multiply two negatives, you get a positive, and 2 times 1/3 is 2/3. I'm not going to change anything in the middle. I'm just going to do the power part. Negative 1/3 minus 1 is what? Negative 1/3 minus 1? Nice. Now, all I've done so far, this and this came from the power rule part of the original problem. Now I have to do the derivative of that 6x plus 3, which is just 6. Can you cancel anything? Like the 3 and the 6? This 3 divides into that 6 2 times. So this 3 is going to be gone, and this 6 is going to reduce to 2. But I'm going to take that 2 in red, and I'm going to multiply it by the 2 in the front. Using not a highlighter. right? You can be done at the top line right there. If it's a free response question, if it's multiple choice, they're probably going to do a couple things. The 4 is going to stay right where it is on the top of a fraction. The 6x plus 3 is going to go to the bottom because it has a negative exponent. Because the exponent is 4/3, you're going to get a cube root because of the 4/3. And this is going to be raised to the 4th power because of the 4/3. Easy peasy.
Are we going to have to do the equations to where you can't write it as like an inverse because there's a function on top? Okay. Yeah.
But you know how to do it. Let's do this one. Oh, you meant with, to get rid of quotient rule. Honestly, once you understand how the chain rule works, unless the exercise is use quotient rule, I think you can rewrite anything with a negative. Any quotient can be rewritten as a negative exponent, and as long as you understand the chain and product rule, you can do it. It may not always be the easiest way, but 100% you could. That's a good question. Very insightful. There's a lot going on here. Let me rewrite it. And here's the confusion, I think. It's this. This cube means that after you do the cosine of whatever you have, you cube that result. So it's probably best when you have a very complicated chain rule to think of that cube on the cosine as being a cube after you apply the cosine. Now, in order, here's what I'm going to do. I'm going to do power rule with that 3, and I'm not going to change anything inside those square brackets when I do the power rule. Then I'm going to multiply, and I'm going to do the derivative of the cosine. And I'm not going to change anything that's inside the cosine. Then I'm going to multiply by the derivative of...
Jake Brown to the junior high office, please. Jake Brown to the junior high office. Thank you.
Of the e, and I'm not going to change anything in the exponent. And then I'm going to multiply by, I'm out of colors, the derivative of that exponent, the 5 theta. I guess I could just make all that because we talked about that rule already. Whew. You know what to do first? Would you be able to look at this and know what to do first? To me, that's tricky. But when I rewrite it, what's on the outside? Yeah. So I'm going to do the 3 power part of the derivative first. There's that. I am not going to change anything inside that exponent. So the cosine and the e to the 5 theta are going to stay exactly the same. All I did was the power rule part. Then I multiply. You know what I'm going to do the derivative of now. So if I start from the cube and then I go inside those square brackets, the next layer in is the cosine. Well, the derivative of cosine is negative sine. Don't change anything that's inside that sine, though, or that cosine, if you will. And then I'm going in another layer. Now I'm going to do the derivative of e to the 5 theta. Well, the derivative of e is itself times the derivative of the exponent. It doesn't matter how complicated the problems get. Chain rule allows you to do the derivative of nearly anything. Nearly anything. You know what that would look like in multiple choice? Yeah, I'm gonna use arrows. I'm gonna start by multiplying those things together. 3 times a negative times a 5. And then I would have the e next. And then I could have either the cosine squared or the sine next. Either one, it doesn't really matter. Probably looks something like that. Oh, just imagine the possibilities. Imagine the possibilities. Let's do a logarithm one. Let me delete all these old notes. I don't want to think later that we did these and we didn't. Nice. When you look at these, are there any of these that you're not sure that you would know how to do? Let's do some mental work real quick. Can I use properties of logarithms to move that -4? Can I use properties of logarithms to move that -4? Yes. Yep, move it to the exponent. Once I move that -4, could I use properties to cancel anything? And then, once I don't have the e and I don't have the ln, could I, this -4 is going to be right here, could I multiply those two things together because the e and the ln are all gone? And then I just have a power rule problem. Did everybody just follow what I said? Do I need to write any of that down? Here, I'll write it down just in case anybody doesn't see it. I'm not trying to, I'm going to use, I really don't want to have to do a massive chain rule problem, so I'm going to start by trying to rewrite this thing. And then I'm going to use a property of, it's the inverse property. It's the fact that E is the mathematical opposite of ln. That property allows me to do this. Those cancel. And so now my problem says x squared times x to the -4. Well, I know how to work that out.
Teachers, please excuse this interruption. The students that are going on the Intro to Education class field trip need to report behind the Ag building, Mr. Faraday and Ms. Pasley's room, to load the bus. Thank you.
And then there's the derivative. And here's the derivative without negative exponents. You can do a little work up front and have a really easy exponent or derivative, or you can do no work up front. And the chain rule on this, you're gonna have a product rule and you're gonna have a chain rule, is gonna be rough. Oh, that's a good one. Do we have one that doesn't simplify like that? Well, would it be worthwhile to do without the simplifications? I guess it's not worth doing that. What about this one? Can we do you can simplify this one, right? Yeah. Do you need that 2 to be in the power position? You can leave it there if you want, or you can move that 2 to the front and then do the derivative. It may be about the same in this case. You know what, I might try doing both ways this time. Might try to do them both. What is the derivative of natural log? In this case, it's 1 over x squared plus x plus 1. So I should have asked the question, what is the derivative of the natural log of something? Well, it's 1 over something. But I'm not quite done. I just did the derivative of natural log, that outer layer. Now I need to move in and do the derivative of x squared plus x. So times the derivative of x squared plus x is, right? You got to go in the parentheses and do a derivative. And then you could clean that up a little bit. You could multiply this 2, this 1, and this 2x plus 1. That's all your numerator. Could we have done it? I wonder if we could do that without rewriting it. What would that look like? I don't know if I'm going to have room, because I'm going to have to do 1 over that thing. Because I'd have to do 1 over all of this, and then I'd have to multiply that by the power rule where I move the 2 to the front, and then multiply that by the... No, I'm not going to have room for all that. How much time? Is this a good time to stop? That's a good time to stop.